First of all, thank you to the organizers for inviting me to give this talk. I think, so we're going to talk about the Motivic coaction and its interplay with dimensional regularization by using cohomology with twisted coefficients. This talk actually is a nice addition to Ruth Brito's talk from Monday. In fact, I also used as the same example throughout. So, okay, so let's start with some definitions. First of all, we'll be considering Feynman integrals in parametric representation, which are integrals of this form, where G is a Feynman graph with VG vertices, EG edges, and EGX legs. D is the number of space-time dimensions, NG is the number of internal edges, and AG is the loop number of G. Now to each edge, to each internal edge EG, we associate a variable alpha E and define the first and second Szymanczyk polynomials. The form omega G in the integral is the standard form on projective space. And the domain of integration is the standard simplex in P in the projective space of dimension ng minus 1, that is the real points of that. We'll only consider convergent integrals for now, and also note that I have dropped the gamma value, which usually goes in front of the integral. And crucially, note that these integrals are families of periods, meaning that they're integrals of algebraic functions over algebraically defined cycles of integration, which vary as functions of the kinematic variables. So now I want to set up some technical details for the Motivic-Galois theory of periods. This will be brief, and we'll soon see some examples how this works with Feynman integrals. So sorry if this is a bit too technical at the moment. So we'll be considering the category H of S of triples, where VB, B stands for Betty, is a local system of finite dimensional Q vector spaces on the complex points of S. V de Rham is an algebraic vector bundle on S with a flat connection with regular singularities at infinity. And C is an isomorphism of analytic vector bundles with connection. We also require that V Betty underlies a variation of mixed Hodge structures, that is, that we have Hodge and weight filtrations compatibilities with C, with the comparison C, and so on. Crucially, H of S is a Tannakian category with two fiber functors, omega de Rham gen stands for generic, which sends an object of H of S to the sections of V de Rham over the generic point of S. I should say that S is here the space of kinematics. That is the complement in the space of kinematics of the Landau variety, but anyway. Omega Betty is another fiber functor which sends a triple to the sections of the local system V Betty over a simply connected open subset of the complex points of S. With this in mind, we can define the ring of Motivic periods as the algebra of functions on the torsor of isomorphisms between these two fiber functors. We can see the elements of the ring of Motivic periods as triples V sigma omega, where V is an object in the category H of S. It's a triple again, and sigma is a section of V Betty. That is, it's a cycle of integration or a family of cycles. And omega is a section of V de Rham. That is to say, it's a differential form or a family of differential forms, more precisely. Now, this ring is endowed with a period morphism, which lands in the ring of multivalued meromorphic functions on S of on the complex points of S with the prescribed branch along Z. Now we can define the Motivic-Galois group, that is its de Rham realization, as the group scheme of automorphisms of the de Rham fiber functor. This group scheme acts on the ring of Motivic periods, or dually, it coacts by its algebra of functions. Now, crucially for Feynman integral applications, Brown in 2015 associated to any Feynman graph with generic kinematics a graph motive, which is an object of this category, H of S, and an element IMG in the ring of motivic periods, such that the period, its image under the period map is the integral, is the Feynman integral itself, with its dependence on the kinematics. Now, we call IMG the motivic lift of the Feynman integral, or the motivic Feynman amplitude, as Brown calls it. Okay, so now for an example. With this in mind, we can consider a box graph like this, with all masses and momenta generic in D equals 4 dimensions of spacetime. We can then state a theorem about the coaction, computing the coaction. And in this theorem, I only want to focus in this talk on the left-hand side here. So these numbers in red, these motivic periods in red here are the motivic Galois conjugates of the motivic Feynman amplitude of the box graph. And by this notation, I mean that they are motivic periods associated to the Feynman graphs, which we obtained by contracting two edges of the box graph. And also D equals 2 stands for the fact that these are the motivic Feynman amplitudes in D equals 2 dimensions of spacetime. Crucially, we note that these motivic periods are associated to subquotient graphs with fewer edges than the original graph. So we can then reasonably ask when a statement like that for Galois conjugates is true, or more precisely, is it always true that the conjugates of a Feynman integral are motivic periods associated to motives of subquotient graphs, with weight of the conjugates bounded by the number of edges of the subquotient graph? If so, this is a very powerful statement. It relates the integral that we started with to the integrals associated to subquotient graphs, thereby providing information and constraints on the original integral in terms of the simpler integrals. Right, so let's consider another example, which is the one from Brito's talk. So we take the 3-point function with one loop, and all internal masses are set to 0, and the external momenta are generic. This is the relevant computation of the motivic coaction on this graph. And again, let's focus on the motivic Galois conjugates on the left here. These are the motivic lifts of logarithms of these quotients, and they're not motivic periods associated to quotient graphs, not directly at least, which is very much expected because the quotient graphs, for example, this one where we contracted the edge number 2, do not converge when the internal masses are 0. Right, so clearly we need to regularize, and we consider dimensional regularization. We set 4 minus 2 epsilon dimensions in our initial definition of the Feynman integral, and we let epsilon vary. That leads to an integral like this. And now we can expand in epsilon and obtain an expansion here, which I call IGL. L stands for local. And we can write the logarithms in the expansion here as algebraic integrals, and therefore see that coefficients, that all coefficients in epsilon are themselves periods. So we can apply then the coaction term by term in epsilon. I put the red M here because I'm assuming that I've lifted the coefficients to the ring of motivic periods so that I can apply the coaction. And a priori, I get a series in epsilon with coefficients which are tensor products of motivic periods and functions on the motivic Galois group, which I'm not going to worry about in this talk. However, the claim is a very strong claim, is that this series actually can be rearranged so that it can be written as a product of two series in epsilon, one having coefficients only motivic periods, and the other having coefficients, the functions on the motivic Galois group. In fact, the conjecture is stronger than that. And in their paper, Abro, Brito, Duran, Gardi, state that it can be rewritten in terms of quotient graphs. Now, in blue here, this is the trivial term. I'm going to ignore that. In red, I have the expansions in dimensional regularization of quotient graphs, that is of the bubble graphs that we just saw, by contracting one edge of the triangle. And in gray, we have the functions on the motivic Galois group, which I would just note that in their conjecture, the Abro, Brito, Duran, Gardi state that these can be related to cut graphs, which would be wonderful, and is actually in the one loop case can be very likely can be made rigorous for the higher loops. I'm not sure. Okay. So let's try to, sorry, I'm just going to go back. So now let's try to make sense of this formula at the bottom here, using cohomology with coefficients. First thing that we do is fix epsilon to be a generic number. In this case, it's not, we require it to not be a half integer. Now this is a bad thing to do essentially, because we want to be able to expand these integrals around epsilon equals 0 usually. But let's go with this for now. First, we want to realize the integral as a period. And period here is in inverted commas because by introducing this epsilon, we are exiting the world of classical periods in the sense of Kontsevich and Zagier. Okay, and let then Q be the vanishing locus of the second semantic polynomial of the triangle graph, and L be the vanishing of the first semantic polynomial, and let them be defined over a subfield of C. That is, we fix the kinematics, we fix the kinematic variables. Then consider a vector bundle, O of X, a rank 1 vector bundle, on the space which is the complement of Q union L in the projective plane with the following connection. Then let L epsilon be a rank 1 local system of flat sections corresponding to the vector bundle just defined. By this I mean there is an isomorphism like this one. And then there is a comparison isomorphism. This is a relative version of a theorem of Deligne, where we have an isomorphism between the twisted de Rham cohomology with coefficients in this vector bundle and the Betti cohomology with coefficients in the local system. D here is the divisor given by the coordinate hyperplanes in P2, that is the coordinate lines, minus the points of intersection with, oh, it's written X here, it should be Q, minus the points of intersection with Q and L. Okay, with all of these defined, we can see that the differential form omega over psi squared, which figures in our integral, is defines a class in the twisted de Rham cohomology, and moreover, the domain of integration sigma g, loaded with the function psi squared over xi to the power epsilon, defines a loaded cycle that defines a class in the Betti homology with coefficients in the local system L epsilon dual. Dual here is because we've passed from cohomology to homology. In fact, to be completely precise, we need to replace Betti homology with locally finite homology. This is because some points of the domain of integration sigma g were deleted. We'll see that in a moment. Were deleted when we when we deleted Q and L, the graph hypersurfaces. And in this case, we can do this replacement. We can replace Betti homology with locally finite homology with impunity for a reason that I will describe in detail in a moment. With all of that in mind, the integral I of G, which is now the dimensionally regularized period, is a coefficient of this comparison isomorphism. And this is what we mean when we say we realize the integral as a period. We write it as a coefficient of a comparison like this. Okay, so now let's study the motive, the relevant motive. And motive again is in inverted commas because we are not in the classical setting. First claim is that this motive sits in a short exact sequence like this. The reason for that essentially is the following lemma that which states that the cohomology of the complement of Q union L in P2 with coefficients in the local system L epsilon is concentrated in cohomological degree 2 and has rank 1. Now, the sequence itself is a long exact sequence in relative cohomology where the lemma implies the 0 on the left. That is that the first cohomology of X with coefficients in L epsilon vanishes. The 0 on the right is implied by Artin vanishing essentially because the space, the coordinate lines minus the points of intersection with the graph hypersurfaces are an affine space, are affine spaces, and therefore everything above H1, above the dimension, vanishes. Okay, so because this lemma is it's a crucial tool which makes the cohomology with coefficients so useful and sort of easier to work with in a certain way than the standard one. I'm going to go into a brief sketch of the proof of this. So let J be the natural open immersion and the inclusion of X into the projective plane. Then if epsilon, as we've required, is not a half integer, we have this isomorphism of local systems. Actually, it's an isomorphism of in the derived category of sheaves on P2. It's much more. It's more general. It's true whenever the monodromy of the relevant local system doesn't have 1 as an eigenvalue. Now, essentially, because of this isomorphism and because of how cohomology with compact support is defined, we have an isomorphism between the cohomology of X with coefficients in the local system L epsilon and the compactly supported cohomology of X with coefficients in L epsilon. Now we can apply Poincaré duality, which is stated here in the generality that we needed in, which is to say for cohomology with coefficients in local systems, and by Artin vanishing, which is stated here that I just mentioned before. So everything above K equals 2 vanishes. These two together imply the first statement that the cohomology is concentrated in degree 2. Now, the fact that it's rank 1 comes from this very easy statement that the Euler-Poincaré characteristic of twisted cohomology with coefficients in a local system is equal to the rank of that local system times the standard Euler-Poincaré characteristic of the space. In this case, this is just 1. Right, so actually point 2 here is very important because from it, it follows also the statement about replacing homology with locally finite homology with impunity also follows. Also from that, intersection pairings and other interesting things that people have been studying recently in the context of quantum field theory and string theory has been, it also follows from that. Okay, so back to the motive. This is the short exact sequence that we're looking at. Now let's look at the left-hand side, or what are known as the boundary motives. Now these are, if we look at how they're defined, they are isomorphic to H1 of P1 minus 3 points with cohomology in this local system that we've defined, except we are restricted obviously to the boundary. We can notice that this is a beta motive up to a twist. By this I mean essentially it's a rank 1 motive whose period is what I've written here. It's a beta function evaluated at minus epsilon comma minus epsilon with a prefactor of a momentum square of momentum squared to the power of minus epsilon. For much more generality in this direction, you can see a very nice article of Brown and Dupont from 2019, which studies generalized beta integrals in this generic setting with these fixed generic parameters, and also talks about the coaction there and so on. Right. On the right-hand side of the short exact sequence, we have this object H, second cohomology of the complex of Q union L in the projective plane with coefficients in L epsilon, and I claim that it's a C to the power epsilon twist for a constant C. Constant C is a rational function of the momenta, which I didn't write it here, of a pure Artin Tate motive of weight 2. This just means that it's isomorphic to the standard Tate motive of weight 2 multiplied by C to the power epsilon. After a finite extension of the field of coefficients, that is, which just comes from the fact that Q and L intersect in a non-algebraic, in a point that's, in points that live in a quadratic extension in this case. Of the field of coefficients. Anyway, let's look at the period matrix for this motive, which is much more concrete than what I just said. On the diagonal here, we have the beta functions that we've just seen, multiplied by an epsilon power of the momenta squared, minus epsilon power. Why is it? Oh, it's minus epsilon. Yes, this is fine. Right, these correspond to the boundary components, and then the zeros above the diagonal are there because we have a direct sum of twisted beta motives on the left-hand side of the short exact sequence, if you remember. In the column on the right, we have 3 integrals, I1 to I3, which could be integrated directly, but we don't need to do that because we're just talking about the Galois coaction. So I'm going to skip that for now. And finally, in the bottom right, we have the C to the epsilon times 2 pi I. This corresponds to the Artin Tate twisted motive that we've just seen. Okay. Now, the Feynman integral is a linear combination of the I1 through to I3 with coefficients, again, rational functions of the momenta. Now, we didn't define a Galois group and an action in this setting, but we could have done, and you can see Brown and Dupont for an ad hoc definition of the Galois group for this setting. However we defined it, the conjugates of the Feynman, of the dimensional regularized Feynman integral would be precisely these beta functions twisted by the momentum squared to the power of minus epsilon. And of course, there will be a trivial term that will correspond to this C to the epsilon times 2 pi I. Now, this is because essentially that's how Matija Galois groups work. The conjugates will always be found in the motivic periods. The motivic periods in the coaction will always be found in the period matrix of the given associated to the given motive. Now, let's expand, even though this is an illegal move now because we've fixed epsilon to get to this period matrix. But for the sake of argument, I don't know, let's expand this expression of q squared to the minus epsilon times b minus epsilon, beta minus epsilon. On the left, we get this the first two terms look like that. For the beta, the first two terms look like that, and we get something like this minus 2 over epsilon plus 2 log of qi squared, and so on as the first terms in the expansion. Now this was observed, although I might be wrong about a factor of 2 here, and possibly a minus 1, but maybe I was a bit careless there. But in any case, the shape is correct, and this was observed by Abreu, Brito, Dürr, and Gardi in their paper to correspond to the first few terms in the expansion of the bubble integral with trivial internal masses and in Dirac. Right. The reason this is true can be quite obvious if we look at the geometry associated to the triangle graph. So here we have the quadric Q, which is the vanishing locus of the second semantic polynomial, and a line L. Now, the three coordinate lines here are given by the vanishing of the coordinates alpha, and it's very important to note that the quadric Q goes through the corners here. Now, each of the coordinate lines corresponds to the geometry associated with the three bubble integrals when the internal masses vanish, that is. This is due essentially to the factorization properties of the semantic polynomials. Okay, now let's have a quick look at a broader picture and what needs to be done in order to kind of complete this line of reasoning. So we started with objects like this one here, the cohomology of x comma d, where d is a divisor in x, with coefficients in some local system L epsilon. However, we fixed the epsilon to be a generic complex number to do our computations, and in fact what we want to do is to be able to expand in epsilon. So we need to make epsilon vary, and this leads to a concept we call global Mellin motives. This is because it addresses its period. Their periods are integrals like the one on the top right here. F to the epsilon can be replaced with multiple functions as well. It can be f1 to epsilon 1 through to fn to epsilon n times omega. Omega is a differential form, obviously. Now, the reason they're called Mellin motives are because the periods are of this form. But if we allowed the kinematic variables to vary as well, then those should probably be called hypergeometric motives. The motives associated to those periods should be called hypergeometric motives. Now that we have epsilon that varies, we can take an expansion around epsilon, and this leads to the concept of local Mellin motives, whose periods are the expansions on the right here. Now, both of these, both global and local parts of the picture, should correspond to Tannakian categories, should be the global Mellin motives and the local Mellin motives should be Tannakian categories, each of which has a Tannakian Galois group attached to it, with a functor localized between them, which should enable us to compare the coaction before and after expanding in S. This is what leads this should lead to our ability to resum the series in such a way that they factor, like we talked about before. This is a topic of upcoming joint work with Francis Brown, Clément Dupont, and Javier Frezan. The local picture is already fairly well understood, in fact, this category of local Mellin motives is very closely connected to the classical category of motives, or classical conjectural category of motives. While the global picture is much more out there, kind of. In any case, there is no reason for this to be limited to one loop graphs. As you can see here, any integral of the sort on the top right will do. Right. However, when we go beyond one loop graphs, I would say that it should be more difficult to interpret the right-hand side of the coaction. That is the coaction. That is the functions on the Motivic-Galois group that appear there. This is to do with the cut graphs in the conjectures of Abreu, Brito, Dur, and Gardy. Okay, so I've basically explained the main points that I wanted to explain. So I just look at another for the final few minutes. I would just look at another example of this phenomenon. So this also appears in several places relating to hypergeometric motives. This example, which is this integral from 0 to 1 of x to the power s a dx over 1 minus ax, where a is a fixed complex number that's not 0 or 1. The expansion here is when we expand this integral around s equals 0, we get this infinite series of polylogarithms. And okay, so this integral, by this integral I mean the integral 0 to 1 x to the power s a dx over 1 minus ax, is a period of this motive M here, where ls is oh, this is not written well. Ls here corresponds to the vector bundle ox, and the connection is d plus s times, this should be d log x here, on the space a1 minus the inverse of a. Now this motive sits in a short exact sequence like this. We essentially, one does the same analysis, the same analysis that we did in the triangle graph case, and we finds that this motive sits in a short exact sequence like this, and moreover that the period matrix looks like this. So here again in the bottom right we get this twisted 2 pi I twisted by some constant to the power minus s here. Should be minus s. No, that should be s, I think. Anyway, let's look at the local expansion and see what happens term by term. If we lift the expansion to Motivic periods, just assume that we've lifted it, and we coact term by term on these polylogarithms here. The coaction of polylogarithms is well known by the work of various people, Contra, Vihara, Brown, and so on. And moreover, we also must coact on S by dividing it by this L-Deram inverse. Now, L-Deram is one of these functions on the Motivic-Galois group, and in this case, we have also removed the kinematics completely. We are not talking about final graphs anymore. We've fixed S in the previous construction to be just a point. So if we do this and we apply the coaction on polylogarithms directly, we get an ugly formula like this. However, then the claim that I was talking about, the claim that it factorizes, leads to the following. We can notice that this can actually be rewritten with just two terms. One tensor, the RAM version of the same thing defined up here, and then the original series, the original local expansion tensored with this here. This thing on the right. These are again the functions on the Motivic Galois group. Now we have defined here this twisted AS local expansion with the RAM logarithms. The important thing to notice, well, two things. One is that these two terms exactly correspond to the Feynman, to the period matrix that we've just seen. It was a 2x2 matrix of the motive with twisted cohomology. And the second is that we also coact on this expansion parameter S. Sorry, by the way, for switching epsilon for S in the middle, at the very end here. But this didn't have anything to do with Feynman integrals, so I forgot to change it. Anyway, this S is clearly also an object that must be coacted on, and that's because it also belongs to this category of objects which are the functions on the Motivic Galois group. And in fact, from this expression, we can conjecture that it's of weight -2. This is in fact understood by now. We know why, and it is a Durham. It is an object like that of weight 2. Yeah, I'll just conclude by saying that this is something this is a set of ideas that coming from Feynman integrals in dimensional regularization that's very exciting from the algebrogeometric point of view, because we have the situation where the coaction on infinitely many periods, like in this equation on the bottom, we have infinitely many periods, but it's can be rearranged into a finite expression and understood using these very convenient tools of cohomology with coefficients. So, okay, that's it. I would stop there, and thank you very much for your time.
Thank you, Matija. We have time for a couple questions before the break in discussion. I see Eric. You have a
Hello.
Answer.
Hi. Can you hear me?
Yep.
Yes, I can.
I was wondering. So you explained that. So in the triangle example, I understood that without the dimensional regularization, the problem is that you don't have periods associated to the bubbles to match to the coaction, right? And once switching on the dimensional regularization, this works with these beta motives. Now, in general, I was wondering the fact that all these terms in the coaction are associated to quotient graphs. I mean, is there a general expectation that this should always be the case? Because I could imagine situations where you have two independent periods, say, or a higher rank part that does not come only from boundaries.
Right. So the question is, yeah. So indeed, so this is the problem with the coaction without dimensional regularization, with the triangle with internal masses vanishing. What happens is that the periods move away from the boundary, kind of they jump somewhere else in the cohomology of the relevant motive. So I suppose what you're asking is does dimensional regularization move all the periods back to the boundary, and why would we assume that? Well, I'm not sure, to be honest. I would think that the fact that well, these factorization properties of the semantic polynomials, I think, show that you should always have you should always have the periods on the boundaries, except that sometimes these will diverge, so they won't. Yeah. So anyway, if you think about if I think about it in terms of periods and this geometry, I can't see how I could have periods moving away from the boundary because of the subquotient divergences. Or do you have in mind something different, where periods appear for some different reason, appear in the
I was thinking of a situation just where I don't know, I have a very complicated geometry, I have a very high rank, and maybe I don't have a super complicated boundary. So I just think in general.
Oh, I see. So okay,
convinced that I have enough stuff from the boundary to fill out everything.
Yes. Okay. So let's see. So already in the sunrise graph example. So for the sunrise graph, there will always be two periods that don't come from the boundary. There will be two. So because the cohomology of the elliptic curve, that is given by the second semantic polynomial in the sunrise case, because the cohomology of the elliptic curve is rank 2 and not rank 1, there will always those two periods will always be, they won't be on the boundary, obviously, and so yes, then in that case the motivic Galois conjugates you won't be able to write them in terms of the subquotient graphs. They're just related to the graph itself, to the original graph itself. It's kind of difficult without being able to write. Is this an example like what you had in mind? Yeah, okay. In the chat, yes, thank you.
We also have a question from Ruth.
Mm-hmm.
Ruth, go ahead. Ruth, your microphone is on. Okay. Well, seem to be having some technical difficulties there. Another sec. For the break and discussion.
Okay, can
and
because I cannot
yes?
raise hands since I'm an organizer.
Oh yes, please.
Hi, Matija.
Hi.
So I was wondering, so at the end of your slide, you mentioned these global local Mellin motifs.
Yes.
And the definition you showed, well, at least, so I don't know much about the topic, but it looked very similar to what other people call these like motivic gamma functions. So is there any connection to that? Or?
Yes, there is a connection, but so this story is oh, there's Ruth. Okay, so I'll answer Claude's first, and then I'll come back to Ruth. Yes, they're the same types of integrals in both settings. However, there is so if we look at, for example, a recent paper of Spencer Bloch and Masha Vlasenko on these gamma function and a priori constants and so on. These a priori numbers and whatever. This is a slightly more general. No, not slightly. This is a more general. It's a more general setting than what I was talking about here. They kind of generalize and then specialize to to something else. However, these things are related, and it could be. I don't have a very good, without talking about relative completions of fundamental groups and things like that, and of spaces. I can't really explain where the generalizations and specializations are, but yes, the answer is that there is definitely a relation. This should be simpler. This way that we're looking at it should be simpler to understand at first. I mean, I'm fairly confident, and for example, for Feynman integrals, we can write down motives, these new Mellin motives of Mellin motives associated to Feynman graphs, and that should be pretty straightforward in terms of the geometry that and graph hypersurfaces and so on, things that we're used to in projective spaces. So that would be the comment for that. Is that okay?
Yeah, thank you.
Okay, and for Ruth, I just wanted to ask whether there are particular obstacles looking at elliptic integrals. No, there are no. So as I said, any integral of the shape that I've shown works. So in particular, any Feynman integral in DIMREG. It won't be as easy to write nice expressions for the coaction for elliptic integrals because of two things. One that Eric mentioned. So for example, you will have multiple periods you could have multiple periods as the conjugates that are related to the original that don't come from the boundary, therefore they can't be expressed in terms of subquotient graphs. That's one thing that we have to kind of come to terms with. And the other is that the Durand periods, the right-hand side of the coaction, and expressing and relating that to actual integrals and not just functions on the Motivic Euler group, that step might be also a bit more, no, it will be more tricky because, well, there are technical reasons.
Okay. Well, let's thank Matija again, and we will return to hear a talk by Matthias Volk at 16:15.
Thank you.
Thank you.
Matija, maybe I can ask you a question as well.
Oh, sorry, real quickly.
Oh, but that's okay. I mean, I didn't want to. It's just so. What I mean, it's not. You can have you could have left-hand entries that are not related to quotient graphs. Also, if it's not elliptic, right?
Yeah.
Okay. Okay. Great. Okay.
Yeah.
It's nothing to do with it being elliptic or not, right?
No. Absolutely.
Okay.
Yeah.
Okay.
What Eric said. Anything that where not much comes from the boundary, it kind of has a rich geometry just directly associated to the, for example, to the graph hypersurface. That is.
Okay. Okay.
So not the domain of integration and its intersection with the graph hypersurface, but the graph hypersurface itself. If that has a rich geometry and a cohomology of high rank, then whatever the rank of that is, that will be the number of periods that you relate to the subquotient graphs. Yes.
Okay. Okay. All right.
Jacob, can you hear me?
Yes.
There was a question from Stefano, but he was having difficulty raising his hand. We older people are not very. So Stefano asked a question of my talk, which I'd like to briefly answer here because it's a fascinating one to me, and that is that we're looking at regular points of the Calabi-Yau differential equation where there's extraordinary modular properties. Why are there just two of them? Why just these two algebraic numbers? Could there be more? And there's been quite a lot of investigation of that. And we do it by looking at the local factors of the primes of the L functions in the generic case. When the parameter is any algebraic number, and you look to see whether or not you have factorization of the local factor, which we do in the modular case. And so they investigated a huge number of rational and algebraic numbers, and they only found these two special values, the ones I began my talk with. So I think we have an extraordinary situation. I mean, it's something I think unexpected by the algebraic geometers as well as by the Feynman diagrams. It's been very thoroughly investigated. If you find another one, please tell me.
Thank you, David.
Any other questions for either of this the first session's talks? Okay, if not, we will reconvene at 16:15. Thank you, everyone.